In this tutorial, we're going to look at differentiating x to the power n from first principles. Now, n could be a positive integer, n could be a fraction, it could be negative, or it could be 0. So we're going to start by taking the case where n is a positive integer. So we'll be looking at things like x squared, x to the power 7, even x to the power 1. So we have y equals x to the power n. Our definition of our derivative function is dy by dx equals the limit as delta x approaches 0 of f of x plus delta x minus our function of x divided by delta x. So let's just look at this part. First of all, our f of x plus delta x is going to equal x plus delta x all to the power n. And this is a binomial. So what we're going to start by doing is actually just expanding a plus b to the power n. And that is a to the power n plus n times a to the power of n minus 1 multiplied by b, plus, and there are lots of other terms in between, both containing powers of a and b, along to our final term, which is b to the power n. Well, now let's look at what we've got. Instead of our a, we've got x, and instead of the b, we've got delta x. So we've got x plus delta x to the power n. So our a, we've got x to the power n plus n x to the power n minus 1, and our b is delta x plus, and again all these terms which will be in terms of x and delta x up to our last term, which is delta x to the power n. Now let's substitute this into our derivative here. So our dy by dx is the limit as delta x approaches 0 of our function of x plus delta x, which is x to the power n plus n x to the n minus 1 delta x, plus, and again all these terms in both x and delta x, plus delta x to the power n, minus our function of x, which is x to the power n, or divided by delta x. Now here we have x to the power n, take away x to the power n. So our derivative is the limit as delta x approaches 0 of nx to the n minus 1 delta x plus all the terms in x and delta x plus delta x to the power n, all divided by delta x. Now all these terms have delta x in them, and we're dividing by delta x, so we can actually cancel the delta x, so that we have the limit as delta x approaches 0 of n x to the power of n minus 1 plus, now all these terms here have delta x squared, delta x cubed, and higher powers all the way up to delta x to the power n. So when we've divided by delta x, all of these have still got a delta x in them, up to our final term of delta x to the power of n minus 1. So when we actually take the limit of delta x approaches 0, all of these terms are going to approach 0. They've all got delta x in them, so they'll all be 0. So our derivative is just n times x to the power of n minus 1. So our derivative of x to the power n is n times x to the power of n minus 1. Let's have a look at some examples. Let's say y equals x squared. So our dy by dx equals, well, the power comes down in front, so it's 2 times x to the power of 2, take away 1, which gives us 2 times x to the power 1, which is just 2x. Y equals x to the power 7. dy by dx equals, the power comes down, 7 times x to the power of 7 minus 1, so we get 7x to the power of 6. Now, what happens when we have y equals just x to the power of 1? Well, we already know the derivative of this, but let's see how it fits with the rule. Bring down the power, 1 times x to the power of 1, take away 1. So we have 1 times x to the power of 0. Well, x to the power of 0 is 1, so it's 1 times 1. So we end up with the derivative of 1, which is exactly what we expected, because we know the gradient function of y equals x is 1. So that was when x was a positive integer. What happens when x is 0? Well, let's have a look. Y equals x to the power 0. Well, we just saw here that x to the power 0 is actually 1. And if we find the derivative of y equals 1, well, y equals 1 is a horizontal line, so the derivative is 0. So y equals x to the power 0. When n is 0, the derivative is 0. Let's have a look at some more complicated examples. Let's try y equals 6x cubed minus 12x to the power 4 plus 5. So dy by dx is equal to, we have our 6 multiplied by 3 as we bring the power down, x to the power, take 1 from the power, minus 12 times, bring the power down, 4, x to the power of 4, take away 1, and our derivative of 5 is 0. I'll put the plus 0 there. So 3 6s, 18, x to the power 3 minus 1 is 2, minus 4 12s, 48, x to the power 4 minus 1 is 3. So there's our derivative. Let's try another one. Y equals x minus 5x to the power 5 plus 6x to the power 7 plus 25. So our derivative, dy by dx, equals, now this is x to the power 1, so 1 times x to the power 1 minus 1, minus 5 times, bring the power down, 5 times x to the power of 5 minus 1, plus 6 times, bring the power down, 7, multiplied by x to the power of 7 minus 1, plus the derivative of 25, again 0. So we have 1 times x to the power of 0, which is just 1, minus 5 5s are 25, times x to the power 5 minus 1 is 4, plus 6 7s, 42, times x to the power of 7 minus 1, which is 6. Now, we've proved this result when n is a positive integer, but it actually works also when n is a fraction or when it's a negative number. Now, we're not going to do the proof of this because it requires a more complicated version of the binomial expansion, but we're still going to use the result. So let's have a look at y equals x to the power a half. Our dy by dx is going to be a half, as we bring down the power, x to the power of a half take away 1, which equals a half times x, and a half take away 1 is minus a half. Let's have a look now when n is a negative number. So y equals x to the power of minus 1. So dy by dx equals, let's bring the power down, minus 1 times x to the power of minus 1, take away 1. So we have minus x to the power minus 1 is minus 2. Now, before we finish, let's look at two more complicated examples where we need to do a little bit of rewriting in index notation before we can carry out the differentiation. So let's have a look at y equals 1 over x plus 6x minus 4x to the power of 3 over 2 plus 8. Now we need to rewrite this in index notation so that we can easily differentiate it. So that's x to the power of minus 1 plus our 6x minus 4x to the power of 3 over 2 plus 8. So let's differentiate. Dy by dx equals, bring the power down, minus 1, x to the power of minus 1, take away 1, plus derivative of 6x to the power 1, that's 6 times x to the power 1 minus 1, minus, now 4 times 3 over 2, multiplied by x to the power of 3 over 2, take away 1, plus the derivative of 8, which is 0. So here we have minus x, minus 1 is minus 2, plus 6x to the power 1 minus 1 is 0, which is 1, so it's just plus 6, minus 3 fours are 12, divided by 2 gives us 6, x to the power of 3 over 2 minus 1, so that's 1.5 minus 1, so we end up with x to the power a half. And there's our derivative. Okay, one more example. Y equals 4x to the power of 1/3 minus 5x plus 6 divided by x cubed. Now again, we've got a mixture of notations, and to differentiate it, we need to write it all in index notation rather than having the division. So this will be 6x to the power of minus 3. So our dy by dx equals 4 multiplied by the power, which is 1/3, x to the power of 1/3 take away 1, minus, this is 5x to the power 1, so it's 5 times 1 multiplied by x to the power of 1 minus 1, plus 6 multiplied by minus 3 times x to the power of minus 3 minus 1. So let's tidy it all up. We get 4/3. X to the power 1/3 take away 1 is minus 2/3. So it's x to the power of minus 2/3 minus, now here x to the power of 1 minus 1 is x to the power 0, which is 1, so it's just minus 5. 6 times minus 3 is minus 18, and x to the power minus 3 minus 1 is minus 4. So there's our derivative.